Okay, I'm just going to explain a bit about how RTran works underneath the hood. It's going to be quite a high-level overview, and it's intended for people with some familiarity with transport modelling already, just to give them a sort of intuitive feel for how RTran works. Basically, the first point I should make is that RTran works off a really simple grid structure. So the area that you're modelling, whether it's a city or a smaller area, is always divided up into equally sized cells. So they're the traffic zones for analysis. This is done just so that input is easy in an Excel spreadsheet and output is easy in an Excel spreadsheet. So as you see on the map here, this is a city with equally spaced grid cells. This particular map showing the number of trips from each of these zones. So one of these little squares is a travel zone, and the colours here are showing the number of trips from these central zones is higher than the number of trips from the far zones. So this is an input. This would be an input to RTran. So that's the first point. Basically, it all works off a grid structure. Each travel zone is the same size grid, same size. The next point to make is that there's no explicit road structure in RTran. At least the topology of the road network is not explicit. It's implied, and the implied road network structure is always that adjacent cells are linked. So it's basically from this grid is connected to the grid to the north, to the south, to the east, and to the west. So, and that's true for all the other squares. You can knock out individual squares, so you can eliminate those roads. I won't go into that here, but by default they're all linked. The assumed network structure is all adjacent squares are all linked by roads. You can specify speeds and capacities on those roads, so congestion modelling is done given speeds and capacities, but I won't talk about that here. The way that RTran works is just off generalized costs. So there are basically 5 different modes in RTran: train, bus, car, walk, and cycle. But the bus and the train are kind of combined into a single choice called public transport. So they're sort of combined generalized cost of public transport depending on buses and trains. And cost, I'm just going to show you a generalized cost map just so you see sort of what it looks like in the grid cell structure. So let's say generalized cost by car from cell x equals 1, y equals 1. So that's this cell down here, x equals 1, y equals 1. And it shows you the generalized cost from this cell to all other cells. So the generalized cost is, just, in this case, it's saying that it's low generalized cost, so the blue areas show low generalized cost, and it's high generalized cost in the warm areas over here. Just out of interest, the generalized cost to here is high by car just because there's parking charges here in the example that I'm running at the moment. So generalized cost is used for all modes and is used to do the mode split calculation. So if you're traveling from here by car, this is what the generalized costs look like by car, and that's the usual thing. It's the monetary and non-monetary costs all rolled up into one thing, the generalized cost of travel by car. And we can look at the generalized cost of travel by public transport from x equals 1, y equals 1, so from this square. And you see the map looks a little bit different, but we still have generalized costs. And it's by comparing the generalized cost of car and the other modes that we get a mode split between each origin and destination. So it's just a simple multinomial legit choice model using the generalized costs. You can use the tiny GIS viewer to look at the generalized costs, but that's how mode split's done. The other one is the destination choice model. So when you can run RTran in a couple of different ways. One way is to fully specify the origin and destination trip matrix. And I'll just talk about that. So I'm just going to talk about the case where you fully specify the number of trips from each zone and the number of trips to. So in this case, I'll just show you what that looks like for the example I've set up here. Inputs, I'll do trips from. So this is what I've specified. There's a large number of trips from these central zones. because basically this is a city with more population concentrated towards the centre. So I've specified how many trips there are from each zone. I've specified the number of trips to each zone, also called activities, and it looks similar again because there's more jobs and people in the centre. So this is a standard monocentric sort of city that I've set up for this example, and I've fully specified the trips from each square and trips to each square. You could specify them in any way you like, so you just need to change the input spreadsheet. You could specify that most of the trips are to a region out here in the northwest, and most of the trip origins are down here in the northeast. You could do whatever you like, but for this example I've specified trips from and trips to be fairly similar. So that tells us how many trips are from each zone and how many trips are to each of these zones, but we need to turn that information into actual trips. So we need to work out how many trips there are between this zone and any other zone. And that's done with the destination choice model. And I'll just select a random one. I'll choose that square that I chose before, x equals 1, y equals 1. So that's the square down in the bottom left of the screen here again. So this is the result of the destination choice model, and it tells you rather unsurprisingly that places that are closer are more likely to be travelled to. So if you want to think about this heat map here is showing you as the probability of a trip originating in this zone being to one of these other zones. So most of the probable destinations are close because the generalized cost is low. Where there are lots of activities, the probability is also high. So the probability of a trip is governed by, again, a multinomial legit model where the probability of traveling to the destination is a combination of the generalized cost of traveling to the destination, that explains why the close ones are more probable, as well as the number of trips required to that destination. So we need to satisfy the trips, the constraint that we've specified the number of trips to each zone, and that's why these central squares are higher as well, because we've specified the number of trips to that zone. So we have all that information. We know the number of trips from each zone, we know the number of trips to each zone, we work out the trip probabilities using a destination choice model, and we work out the trip modes using a mode choice model. Both of those are just multinomial legit, and they're based on the generalized costs of the different modes. And that's basically how the full trip table is generated. So from that we can calculate the number of trips between each square. And that's what this destination choice shows. The last thing I should mention is that in RTran, whatever period you've chosen to simulate, could be all day, could be just a peak period, all the trips are assumed to be two-way trips, so they're return trips. So just for argument's sake, if you've set up your input sheets so that there's some parking costs in the middle here, and in this example I have, so there's some parking costs in the center of this city, there'll be a return trip, which is a trip from here to the city and back, and that return trip by car, the generalized cost for that would include parking costs at both ends. There's no concept of a tour or whatever, so we don't allow multi-leg trips in RTran. So it's not possible, for example, for a trip to start here, to go to here, then to make a stop off here, and then a stop off here, and then back home there.